Okay, let's work through the example 8.2 that's tied to section 8.7, power output from a three-phase generator. Put some numbers on this, look at some values, calculate power, and then see how we will most likely approach many of these problems in terms of solving the circuit in terms of one phase, and then just considering that there are three of those circuits, right? There's three phases. So anyway, let's look at some of the techniques that we're going to use to be able to simplify three-phase circuit calculations. Okay, so in this example 8.2 that's in on page 163, says I have a three-phase generator as shown in figure 810A, and it's connected to three 20 ohm resistive loads. Okay, so we see those there in our problem, and it also tells us that based on the construction of the generator that we are generating or inducing 120 volts in each phase. And again, we know that these phases are 120 degrees out of phase, but that doesn't really enter into this problem. So the first question, or part A in the problem, it's asking us what is the value of the power dissipated in each resistor. So all you want to do when you're working a problem like that, let's just look at this as a singular problem. Okay, and that's pretty straightforward, right? I got 120 volts and I got a connection to a 20 ohm resistor, and I want to understand the power that's dissipated by that resistor. Well, I have three power formulas that I could use, and the simplest one to use would be the one that I don't have to do any calculations on, because I'm given the voltage and I'm given the resistance. So why don't I use this power formula, and I would take 120 volts and I would square that value. I would divide it by 20 ohms, and this would be 12 is 144, 20, Anyway, let me flip over, because like so many things, I can't do that in my head anymore. That's 720 watts. Okay, in this resistor. Now, just to make my point here about this, if, for instance, I wanted to know what the, if I wanted to use this form of the power formula, if I have 20 ohms and 120 volts, 20 into 120 will go 6 times, and I would have 6 amps flowing through that circuit. And if I used the first version of the power formula, I would say 120 volts times 6 amps, and I would get 720 watts there as well. And of course, I could do the same thing with this. I could take the current squared, which would be 36 times 20, and I would get 720 watts there. So, each one, gets us to the same place. And I agree with Mr. Wildy there that the easiest thing is to just use the values that you're given, and we were given voltage and resistance, so that's what we did. Okay, the second part of this says, what is the power dissipated in the three-phase load? Well, okay, just think about it. One load is dissipating 720 watts, and we have three of those, right? So the total power is going to be 3 times the individual phase powers. So it's 3 times 720. So the total power that is dissipated by the load is 2,160 watts. Another way to phrase that, and you might see it phrased this way: what is the power generated? Whichever way that it's given to you, it's the way that you want to answer it. The next question there, part C, says, what is the peak power dissipated in each resistor? Now you have to be careful with this. We know that these are effective voltages and effective values that we're working here. And so maybe your first impulse there is, okay, well, the total, how does he phrase this? He says, what is the peak power dissipated in each resistor? Well, okay, maybe it's 720 watts per, and that's an effective value. And so I just want to multiply that by square root of 2. No, you can't do that. Mathematically, that is not sound because this is derived from these values. Okay, so I can't simply multiply the power that's derived from effective values by square root of 2 to get peak. What I have to do is I have to determine the peak voltage. Okay, so this is an effective voltage, 120 volts, and I have to take the square root of 2 times that to get the peak voltage, which is 169.7 volts. The peak current, this is again, since this is an effective voltage, then this is effective current, and I have 6 amps times square root of 2, and the current that is associated with that would be 8.465 amps. Okay, so from effective to peak, multiply by the square root of 2. Now I have the peak power in each resistor. The peak power in each resistor, M piece of M, is going to be 169.7 times the current, which is 8.485. I had 6.5 here, apologize, it's 8.5. And if I multiply that out, the peak power is 1440 watts. Okay. Now, we're looking at this in terms of, the differences between peak and effective. In our world, most of the time, we want to stay in the effective so that we're not dealing with instantaneous instances. So, this is just sort of an exercise here so that we understand that. And so the peak power in each resistor comes out to be 1440 watts. Now, what is the ratio? The ratio of the total power, which we found to be 2160, to the peak power, 1440. Well, lo and behold, that comes out to be 1.5. Okay, so whereas the power in each resistor pulsates between 0 and 1440, the total power for all 3 resistors is unvarying and equals 2160 watts. Okay, so an interesting little trip there to come to that number of 1.5. That's where it comes from, and that's how that works. When we're looking at these power curves and coming up with these determinations, if you go back here and I won't do this in this video, but if you go back now and you put those values in there and remember that these are effective values and all, you'll see where that 1.5 comes from for the 3 phases. Interesting stuff. Good things. Okay, so that finishes our overall introduction to 3-phase electricity. And now we're going to get into the weeds a little bit with it. And you've probably heard delta and Y, delta, Y, delta, and Y. Now we're going to look at what that actually means. Okay. Now I know some of you guys are in the industrial world and you hear these terms and they're thrown at you all the time. This is a good opportunity for you to learn, exactly what those things mean, and that's a good thing. And depending on how far you go in school, maybe one of the last times you get to get that level of understanding with that. This background is in Scotland, name of a little town called Oban, O-B-A-N. Beautiful place.